In this class, we're going to learn about a recursive process or recursive sequences and algorithms. A process is called a recursive if it refers back onto itself. In general, when we have a sequence, the recursive sequence will always have to have two parts, one or more base cases, and also a formula or a recursion that gives way to compute new terms given already known terms. So you kind of notice that this is very similar in structure to the induction, where we have a base case and then a way to go from the kth domino to the k plus first one. And in fact, recursion has very much the same flavor as induction does. Let's start off by just building recursive sequences and seeing how that works out. So here I have a sequence given to me by recursion. So this is my part 2 of the definition. This is the formula that tells me how to go from term I to term I plus 1. And because I have to start somewhere, I need to know what the first term is. I'm told that A naught is equal to 1. So that is my first term. Let's write that down. Notice that for the next one, I just have to apply the recursive formula. So if I is equal to 0, I can plug in 0 here and 0 here. And what I'm going to get is an expression for A1. I have A1 is equal to 2A0. Let's write that down. A1 is equal to 2A0. Now I can plug in this value for A0, which is 1, right into here. And altogether, I'm going to get 2 times 1, which is equal to 2. In order to compute A2, I'm going to plug in I equals 1 into this formula. And what I'm going to see, of course, is A sub 2 is equal to 2A sub 1. Write that down. A sub 2 is equal to 2A sub 1. And again, I've just computed A1 to be equal to 2, so I can plug that in to my next formula. 2 times 2, I'm going to get a 4. Altogether, we can, of course, continue, and you can see that each next term is composed by using the formula for the recursion and the value of the previous term. Now, you can also interpret this as a general rule. So what this rule is saying is, to get the next term, we need to multiply the previous term by 2. Okay? When you say it verbally, it actually becomes easier to put the sequence together. To get the next term, we have to multiply the previous term by 2. And so here, I now again have the previous term, 4. 2 times 4 is going to be 8. To get the next term, I have to multiply the previous term by 2. 8 times 2 is 16, and so on. In fact, I can already see that what I'm getting is a sequence of powers of 2. So if I rewrite these guys as actual powers, I can try to match the power of 2 that I'm getting to the index of the sequence. So I'm going to have 2 to the power 1 corresponding to index 1. 2 to the power 2 here, 4, corresponding to index 2. 2 to the power 3, which is 8, corresponding to index 3, and so on. So I can actually see that alternatively, instead of having a recursive formula that allows me to calculate only one term at a time, I have an explicit formula. AK is equal to 2 to the power k. So this is what we're going to call explicit formula, because it allows me to calculate any term directly. If I want to calculate, let's say, A10, the explicit formula will allow me to simply plug 10 in for the index, and I'm done. If I want to calculate A10 using the recursion, A10 is equal to 2 times the previous term, which is A9. But I don't know A9. So in order to find out what A9 is, I'm going to have to use the recursion again. So I'm going to have to, instead of A9, have 2 times A8. But I don't know what A8 is yet. I'm going to have to use the recursion again. So it's going to be 2 times 2 times 2A7. But I don't know A7 yet. I'm going to have to use the recursion again, and so on and so forth. So the recursion is a definition that refers back onto itself, which makes it easy to construct sometimes, but often hard to use if you want to compute a term way down the sequence as opposed to working your way up. Just to get more familiar with the notation, let's do a couple more exercises. So I actually, if you're already comfortable with the above explanation, encourage you to pause here and try to figure out the 5 terms for each of the sequence by yourself before coming back to taking a look at how we do it together. Okay, so I'm starting with a naught equals 3, and I am giving this recursive formula. So once again, you can interpret it directly by plugging in the indices, or you can try to interpret it as a rule. Let's try this one with indices, and then we'll try part B with the rule. So A0 is equal to 3. That means that what I have for A1 is I'm going to apply the recursion, plugging in I equals 0. Okay, if I plug in I equals 0, on the left, I'm going to have A sub 1, and on the right, I'm going to have A0 plus 5. So let's write that down, A0 plus 5. And of course, A0 is equal to 3, so 3 plus 5 is equal to 8. Great. What about A2? In order to compute A2, I'm going to plug in I equals 1. On the left, I'm going to have A2, which is what I'm looking for. And on the right, I'm going to have A1 plus 5. A1 is the one I've just computed, which is 8. 8 plus 5 is 13. A3, I'm going to plug in I equals 2. On the left, I'm going to have A3. On the right, I'm going to have A2 plus 5. A2 is the one I've just computed to be 13, so 13 plus 5 is equal to 18. A4 is going to be 23. A5 is going to be 28. And here we've computed the first 5 terms of the sequence. Okay, so simply plugging in the indices, we can get the next term from the previous one. Once again, what I've pointed out before is if you wanted to compute A4, the recursion will tell you how to do it if you know A3. So in order to know A3, you're going to have to know A2. In order to know A2, you're going to have to know A1. In order to know A1, you're going to have to know the base case of A0. The recursion goes all the way down to the base case. Next up, we have this recursive formula. Let's try to do this verbally, where we try to think of what the rule actually is. So the next term, let's maybe subscript them. This is the next term. So the formula says that the next term is equal to 2 times the current term, which is BI, current term, minus 1. And I'm starting with 1. So B naught is 1. The next term is going to be twice this, as we said, as far as the rule tells us, it's going to be twice this minus 1. So B1 is going to be twice that minus 1. 2 minus 1 is just 1. The next term, or B2, is going to be the previous term times 2 minus 1. 2 times 1 minus 1. Still 1. At this point, it's actually clear that we're just always going to get 1. And so that is simply what it is. So if you compute the next one, you'll get 1. If you compute the one after, you're going to get 1. If you compute the next one, you're going to get 1. Let's try the exact same sequence, but with B naught equal to 2. So I'm not going to change my recursion. All I'm going to do is change my base case. Instead of 1, I'm going to see what the sequence would look like if I start with 2. Is it going to remain 2, like the sequence that started from 1 remained 1? We're about to find out. So, again, verbally, the next term is the previous or the current one times 2 minus 1. So, the current one times 2 minus 1. 4 minus 1 is 3. Okay, we're already seeing something quite different from what happened before. Let's see, B2. The next term is the current term, which is 3, multiplied by 2 minus 1. 6 minus 1 is 5. The next term is the current one times 2 minus 1. So 5 times 2 minus 1 is 9. B4 is going to be the previous term, or the current term, times 2 minus 1. 9 times 2 minus 1 is 17, and so on. So what we're seeing is the initial condition, the base value, has a great impact on what the rest of the sequence will actually look like. Whether it remains constant or it grows or it shrinks, we have no idea how it's going to go. The initial term, the base case, is as important as the recursion itself. So make sure that you pay close attention to what the first term is. Next up, we have the following rule. In order to compute the next term, we're going to take the current term and square it. We're going to start with 1. So what are we going to get? If I start with 1, for the next time I am working with my current term, I'm supposed to square it. 1 squared is still 1. For the next term, I'm going to take what I have and square it. 1 squared is still 1. Then I'm going to take this current term and square it again. 1 squared is still 1, and so on and so forth. So this sequence is once again a sequence of all ones. What if I start with C naught equals 2, just to see how that goes? So I'm going to start with 2. For the next term, I'm going to square it. 4. For the next term, I'm going to square it. 4 squared is 16. For the next term, I'm going to square it. 256, and so on. So these terms grow a little bit faster. What if I start with 3? 3. The next one is I'm going to square it. 9. The next one, I'm going to square it. 81. Then I'm going to square it is 81 squared. I can't compute that in my head that fast, and so on and so forth. So what you notice is, once again, the actual first term heavily affects the sequence. So be careful about what the first term is, and don't assume that it's always just going to be 1. It's going to be very different numbers for very different things. The next recursion is quite different. In order to compute the next term, I'm going to take the current term and add the one before. So this is the first time we're seeing indices that go 2 steps back. The next term is the current one plus the previous one. And we're going to start with the initial conditions for the first 2 terms because we have to actually get our feet off the ground. So this is also why in the original definition, it says 1 or more base cases. As many levels as your recursion has, that is how many initial or base cases you're going to need. So we're going to start as suggested with 1 and 1. The rule says in order for me to get the next term, I have to take my current term, fi, and add the previous one, fi minus 1. So 1 plus 1 is 2. In order to get the next term, I'm going to take the previous one and add the one before. 2 plus 1 is 3. In order for me to get the next one, I'm going to take the one before and add the one before it. 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 5 is 13. 13 plus 8 is 21. 21 plus 13 is 35, and so on and so forth. Note that all of these sequences actually do go on forever. The recursion doesn't stop at any particular term normally. It defines an infinite sequence. Here, the interesting part of this was the fact that we actually used 2 terms in the sequence in order to compute the following one. Once again, if I were wanting to compute a term somewhere down the sequence, for example, F10, the only way to do it by recursion was to see what the actual terms are. So F10 would be F9 plus F8. But if I don't know F9 or F8 ahead of time, then I would have to apply recursion to each one of these to figure them out. So F9 itself would be F8 plus F7, F8 would be F7 plus F6, and if I don't know F7, F8, or F6, I will have to go even further down into the recursion. So, because it refers back onto itself, it's best to keep the sequence building all the way up, but we will talk about how to get the explicit formula for any term you like down the sequence later in the course. Now, this particular sequence is quite famous. These numbers are what's called Fibonacci numbers. So you might have actually seen them before in various contexts. These appear in nature everywhere. For example, this is the pattern in which the sunflowers grow. These also appear in things like the golden ratio, which is formed by dividing 2 of the neighboring numbers by each other and then taking the limit of the actual division. These numbers are quite interesting because they appear in lots of different problems, and we will certainly see them later on as well. For the next example, what we're going to do is try to think about a function that we've seen before and how, knowing what we want, can we define a recursive formula for it. So we would like to define the factorial function. First of all, so this is going to be f. It's going to be f sub n because we need an actual index to go with it, or f sub I. We're going to need to start somewhere. So remember that 0 factorial was equal to 1. Now, in order for me to compute 1 factorial, all I have to do is multiply 1 by itself. So maybe I'll just leave that as is. In order for me to compute f2, I need to go 1 times 2. In order for me to compute f3, I need to go, let's build up. So 1 times 2 times 3. f4 is 1 times 2 times 3 times 4. And as before, I'm already beginning to notice the sequence. This is f3. So that means that f4 really is f3 times 4. f5 is going to be 1 times 2 times 3 times 4 times 5, which of course then is f4 times 5. f4 times 5. And these are giving me a good idea of what a recursive definition is going to be. All I have to do to compute a factorial of number n is compute a factorial of a number n minus 1, because that in itself will actually be 1 times 2 all the way up to n minus 1, and then multiply the result by n. This is the recursive definition of the factorial. Except we're not quite done yet. Remember that the recursive definition has two parts. This is my actual recursion, but I also need to include an initial condition to go with it because I need to know where to start. If I give you just this definition, you're not going to know what first value to start at. And as we've seen before, different starting values produce very different results. So a recursive definition will always have a recursion itself and then the base case or the initial value for it. And this is our first recursively defined function. Let's practice more on how to actually put together the recursive functions themselves. So here's a very famous example on the number of handshakes. You have n guests at your graduation party. Congratulations, you are graduating. Each person shakes hands with everybody else exactly once. We would like to define recursively the number of handshakes that actually occur. So first of all, let's try to determine an actual initial value. So here I am given that h is the function for handshakes. Let's say there is one person. If there is one person at the party, how many handshakes will they have to perform? Well, they shake hands with everybody else. There's no one else, so they're not going to shake hands. So h of 1 is actually equal to 0. Notice that we can use a subscript or we can use the number of people or the number in the sequence here as an actual argument of the function. Either way is fine. If I wanted to compute, let's say h of 2, I have two people, so I'm going to have exactly one handshake between the two of them. I can, of course, carry on and think about how I can compute, for example, the number of handshakes between the three people. So I have three people, say 1, 2, 3. How many handshakes will they have to perform? These two guys have to shake hands. These two have to shake hands, and these two have to shake hands. So altogether, I'm going to have 3 handshakes here. But of course, going through the numbers isn't going to really help me figure out what the general strategy for shaking hands is. So let's try to approach this a little bit more generally. If I have a number of guests at the party, let's think about one person and everybody else around them. The recursion is going to have to take us at least one step back. So it's a good idea to isolate one of the elements and then think about how that element interacts with all the other elements. That reduces the number of people from n to n minus 1 in this case. And building on the previous numbers is exactly what the recursion is about. So let's say there is one particular guest at the party. Let's call her Ksenia. how many handshakes is she going to have to perform? Well, if there are n people altogether, so let's say there is a bunch of other people, what is going to actually happen is that, first of all, she's going to have to shake hands with everybody else. If there are n people altogether, that means that there is n minus 1 people that are not our chosen guest. So there are n minus 1 handshakes happening here. Let's highlight this. This is going to be n minus 1 handshakes. Now, this is great news. So now Ksenia has shaken hands with everybody, but everybody else has to shake hands all amongst themselves. So now we have to think of them as a group altogether. All of these people have to shake hands amongst themselves. There are n minus 1 people here. In how many ways can n minus 1 people shake hands amongst themselves? Well, h of n defines the number of handshakes for n people. So, h of n minus 1 defines the number of handshakes for n minus 1 people. Notice that we don't need to know how many that is. We simply need to have a notation for it. So let's write that down. So what I have now is, again, I have identified that one special guest. So let's give it a name. Let's say Ksenia, KS, be a guest at the party. She has to shake hands with everybody else, which means that she has to shake hands with n minus 1 people, therefore performing by herself n minus 1 handshakes. And then the n minus 1 remaining people have to shake hands all amongst themselves. People have to all shake each other's hands. And that results in h of n minus 1 handshakes. So what we have altogether is the number of handshakes amongst the n people is n minus 1 handshakes that one guest has to perform, plus the number of handshakes that the rest of the n minus 1 people have to perform amongst themselves. Once again, remember that the recursion always comes with an initial condition. So for the full definition, we actually have to include both of these pieces of information. Next up, we are taking the stairs. You are climbing the stairs, taking 1 or 2 steps at a time. You can do them in any particular order. So for example, if you start down here, you take 1 step at a time, and then maybe you take 2, and then you take 2 again, and you land on the top stair. If there are n steps, we're asked to find the recursion for c sub n, which is the number of different ways to climb the staircase. So there are n stairs, which means that at the end of this game, we're supposed to land on the top stair, and we have notation for this. So for this particular stair, there are cn ways to get there. Now, this is the number that we're supposed to describe recursively in other ways. Excellent. So what are the ways that we could have landed there? Remember that you can take 1 or 2 steps at a time. So in order for us to end up on the top stair, we could have come from the stair right before, right? We could have taken that one last step as just 1 step. Or, in order for us to end up here, our other option was to take a big step, a 2 step at a time step from 2 steps back. So we started here and then we hopped over 1 stair. Those are our 2 choices, right? So the number of ways to end up on the top stair is you either were on the previous step and took 1 stair at a time, or you were on the 2 steps before and took 2 steps at a time. Okay, in fact, let's make this color-coded. So you were either here and hopped over this way, or you were on the 2 steps before and you hopped over this way. Okay, Note that this is similar to what we've seen in the counting section, or means that we're going to be adding both of those cases, because you could certainly not have both happen at the same time. You were either on 2 steps before the last one and took 2 stairs at a time, or you were in the previous but last step and took exactly 1 step. How many different ways could we have ended up on this staircase? So starting from the bottom, what are the different options for us to actually end up here? Now, if there are n stairs in total, then this stair is n minus first stair. And there are c sub n ways to get to stair number n, which means that there are c sub n minus 1 ways to land, starting from the bottom, on this particular stair. Similarly, if this is stair n, that this is stair n minus 2, which means that there are altogether c sub n minus 2 ways for you to go from the bottom of the staircase to this particular stair that is 2 away from the top. So if I am to get at the top stair, I could have gotten it by, first of all, getting to n minus first stair and then taking 1 step, or by getting to the n minus second stair and hopping over a 2-stair step. And that is my recursion. Now, once again, we're going to need a base case to go with it. And in fact, in this case, we're going to need 2 base cases because we are using 2 previous steps to rely on for computing the recursion. So let's compute directly, manually, the values for C1 and C2. So if I am at the bottom of the stairs and there is only 1 stair that I need to reach the top of the stairs, so stair, like the level is 1, how many ways can I get there? Well, I can't take steps of size 2. I can only take the 1 step up, so there's exactly 1 way to do so. If there are 2 stairs, so I'm at the bottom of the stairs and I have 2 steps to go, how many ways can I land up here? I can take 1 step at a time from the bottom, or, so that's 1 way, or I can start at the bottom and take 2 steps at a time, landing on top of the stair. And those are my only 2 options. So altogether, I have 2 different ways to achieve that. Once I have my 2 initial conditions and my recursion, I've actually defined this function. Next up, we're going to talk about n-bit words. This is going to be a little bit more involved. We're going to have an denote the number of n-bit words containing no 2 consecutive ones. Okay, so they can contain 2 ones, they just cannot be consecutive or in a row. We're asked to define the sequence recursively. Okay, just to get some handle on what that looks like, let's do a couple of examples. So if n is equal to 1, I'm looking for words of length 1. Now, they're bit words, so binary digits, so we're not allowed 0s and 1s. So I want 1-bit words of length 1 with no 2 consecutive ones. Well, they're only 1-bit words, so I can't even have consecutive numbers. So my 2 choices are 0 and 1, which means that a sub 1 for n equals 1 is equal to 2. There's 2 options for this string. What happens if n is equal to 2? So now I'm allowed to have 2-bit words. So what do I have? Can have 0, 0, I can have 0, 1, I can have 1, 0, and I can have 1, 1. But I'm not allowed to have 2 consecutive ones, so my last choice is completely out. Okay, not allowed by the rules, which means that a sub 2 is 1, 2, 3. What happens if n is equal to 3? That's the last example we're going to do. So I have 3-bit words. So I'm going to have 0, 0, 0, 0, 0, 1, and you go through all of the options, and then you notice that you actually end up scratching quite a few of them. This has 2 consecutive ones, so this can't happen. So I have to backtrack a little bit. I can have 1, 0, 0. What else can I have? I could have 2 1s. They just have to be spaced out. But nothing else will actually work. So this is going to be out, this is going to be out, and finally, what else am I missing? Oh yes, all ones is also going to be out. I know that altogether there are 2 to power 3 or 8 different 3-bit words, so I've listed them all and I've scratched out the ones that are not allowed, which left me with 5 allowed options. So A3 is equal to 5. Okay, now I'm not necessarily seeing the pattern so far, and these are getting a little bit too complicated to track. So let's try to think about this problem in general. What we're going to first of all do is we're going to consider an arbitrary n-bit word and what or how it's constructed. So if it's n bits, then what I can think of is the placement, right? So I have a bunch of different bits and so on and so forth. Because we are specifically told that we want to define things recursively, just like before, I'm going to try to reduce this case to cases that are smaller, right? So just like, for example, in the party example, I've separated one person and then looked at everybody else. So here, I can separate the last bit and then look at all the previous bits, okay? And in fact, I'm actually going to have 2 very separate cases. Case 1 is going to be if my current string ends with 0. Now, zeros are not a problem here, right? I'm not allowed 2 consecutive ones, but there's no condition on zeros whatsoever. So if I have 0 as my last bit, then the other n-1 bits can be anything at all, right? This can be a 0 and this can be a 1. All of these numbers, as long as they have no 2 consecutive ones, this last 0 does not affect anything in terms of the other strings. So if the string ends with 0 and there are a sub n-1 strings with no consecutive ones of length n-1, then there are a sub n-1 strings of length n that end with a 0. Okay, so the number of these strings are a n-1, and that is because this 0 at the end does not restrict in any way what happens before. By contrast, for case 2, we're going to have that it ends with 1. So we have the exact same picture. Let's copy it over. Exact same picture, except for my last bit is now equal to 1. So what have we here? Now, the number of strings that satisfy my rules on n-1 bits is still a sub n-1, except this one is quite restrictive indeed, because it means that I can no longer have 1 here. So some strings here of length n-1 that are perfectly fine and have no 2 consecutive ones themselves will acquire 2 consecutive ones if my string of length n were to end in 1. So that's not great, which means that if it ends with 1, I also have to consider the digit that came before. So I'm going to actually have 2 cases there. If there is a 1 there, that's not good. If there is a 0 here, then I'm all good, right? If there is a 0 in this position here, that means that I can happily place 1 here without breaking my 2 consecutive ones rule. Okay, now let's travel further back. Because I've already determined that this digit has to be 0, I have no control over that. It means that the number of these strings, just like in this part before, is actually dependent on the number of digits that came before these 2, which means that it's dependent on n-2 digits that came before. So the only way that my string can end in 1 is if it actually ends in 0, 1. Otherwise, we would be introducing 2 consecutive ones, which means that my last 2 digits are determined, and the only degree of freedom I have is in the previous n-2 digits. And how many strings of length n minus 2 are there with no two consecutive ones? Well, there are a sub n minus 2 of them. So that means that the number of strings of length n with no two consecutive ones is equal to the case where they end in 0, which results in a sub n minus 1, or the case where they end in 1, which forces them to end in 0, 1, which means that there are a sub n minus 2 other choices that we can then attach 0, 1 at the end of. And this is my recursion. Again, I'm going to have the actual initial values, and because I am too deep here, I will have to provide two different initial values. So here we go. This is my recursion for this case. Notice that we've actually seen this formula before. The new term is going to be the current term plus the term before that. This is the exact same recursion we've seen here. To end on the last stair is to end on the previous stair or 2 stairs back. Just because it's called C versus A makes no difference whatsoever. But the initial conditions are really quite different, which means that my actual sequence of numbers is going to be different. You'll also recognize this as the formula from the previous page at the bottom here, where we actually had Fibonacci numbers. This is the formula, the same recursion as for the Fibonacci numbers, but we're not going to end up with a sequence of Fibonacci numbers because our initial conditions in the 2 exercises here are not 1, 1. So while the recursion is the same, the initial conditions force it to be a different sequence. A classical fun example of constructing recursions is the problem of towers of Hanoi. It was actually invented by a French mathematician, Edouard Lucas, in the 19th century, which is why sometimes they're called Lucas's towers. But it's supposedly associated with a legend that in a Hindu temple, this puzzle was kept to stimulate the monks mentally, kind of like chess in some other cultures. There's also a legend that in the temple, the number of discs on this tower was very large, and if the puzzle was completed, that would be the end of the world. Thankfully, the number of discs is so large that the puzzle will not be completed for a very, very long time. So what is the actual problem? The problem is we have 3 poles. One of them have discs in decreasing order of radius, and what we want to do is to move all discs from one pole to another. The classical problem is to move them from one pole to the third one, but it really doesn't matter as long as you move them to a different pole. There are exactly 2 rules. You can only move one disc at a time. So you can move this one down and it will end up here. And the second rule is you cannot put larger disc on a smaller one. So we cannot have the case where we have this situation. And that proves to be quite restricting already. Our mission for this problem is, given that there are n discs, we would like to find a recursion, m sub n, for the minimum number of moves required to transfer all discs from one pole to another. So let's see what we can do with a small example. Let's take n equals 3, which means that I have exactly 3 discs on one of the poles. There is many websites that will let you play this game. Here's one of them, Math is Fun website, because math is, in fact, fun. So strongly recommend going here. Here are 3 discs. You can play the problem with more discs if you wish. I'm going to go through an example with 3. The actual problem here tells you that there are 7 minimum moves. So if you do the problem as efficiently as possible, you should be able to move all these discs from one tower to the next in 7 moves. I encourage you to pause the video, try this for yourself, and see if you can get to 7 moves right away. Remember that the actual classical problem has the discs moving from the first tower to the third. Okay, so if I am to move, let's say I'm going to move this disc here and the second one to the middle tower, and now I'm actually out of options, essentially. I can move this disc to the first tower, but that's kind of silly because then I'm kind of stuck, so I'm going to move this on top of the second disc. Then my largest disk can move to the last tower, and then I can plop the first one back. Notice that this is something I am not allowed to do at all, at any time. And I can move the second disk onto the largest one and the final one on top of all of them. And I've succeeded to do it in exactly 7 moves, which is the minimum. Doing it in more moves isn't wrong, but here we're after the minimum amount of moves. The more disks you have, the harder the problem becomes. So let's say I move these 2 over. What's my next step? Well, at this point, I can't move this disk anywhere, so I have to combine the 2 I just moved down. So now I'm going to have the largest disk over there, and now I sort of have options of how to proceed and then see where that gets me. Well, that wasn't very smart because now I can't really do anything. So I already know that I am going to run out of maneuvers before anything. So with more disks, this does become more difficult. So what we're going to do next is let's analyze how we proceeded with the problem with n equals 3, so we can extend that kind of reasoning to more disks on more towers. So I'm going to pictorially represent my disks as the largest one is going to be a big flat. The second largest is going to be a squiggly, and the smallest is going to be a flat line again. Now, I'm only using the squiggly line because I essentially don't trust myself to draw 2 horizontal bars that are clearly different in lengths. Now, we're also going to imagine that I have 3 poles here. I don't want to make the picture too busy, so I'm not going to draw the poles. So here's where we start. I need to move this to the other pole. So I'm going to start by first moving the smallest disk to the last pole here. So my second largest stays in place. Then I'm going to move this second largest to the middle pole. That's exactly what I did in the app, right? So I have the largest disk, the second largest, and the little guy. Okay, haven't moved the little guy. There we go. Now, okay, I'm going to move into here. So again, like I'm imagining 3 poles going on. So now I'm going to move the little guy onto the second one. So the largest disk stays by itself, and then my second largest gets the smaller one on top. And I have now freed up my third tower here, or pole here, right? So I can move my largest disk to that spot. And that is great news because now at least I have the right base in the right spot. My largest disk is now in its final resting spot. Now, it would be nice if I could move 2 disks at a time just onto the largest one, but I can't do that. 1 disk at a time only. So the little one will have to hop off to the side here, and then I'm in this picture. Next up, I'm going to have the second largest move on to the biggest one. Maybe I'll move everything onto the next place. So this means that my middle pole is now going to be empty. So the smallest disk is going to stay over here. And then my last move is to plop the smallest on top of the existing tower, and I'm done. So I started with this configuration. I had 1, 2, 3, 4, 5, 6, 7 moves. And that is exactly what the minimum for that is. Now, amongst all of these, let me maybe separate the columns here with a different color. There we go. Amongst all of these, one interesting thing to notice is this instance of a problem right here. And the reason to notice this is because this is exactly the same problem, but with 2 disks. I have 2 disks of different sizes stacked on top of each other, and I want to move them onto a different pole, right? So this is the exact same problem, but smaller. So this is a smaller instance of my problem. And this is essential to notice in whenever you build recursion, because you want to go back to fewer disks, and this will allow you to do so. So keeping this in mind, let's try to reason out in general how we're going to move all of these disks. So just so that we can refer to them, let's call the poles A, B, and C. We're going to think about the last move we're going to make. Think about how on the previous page we thought about, for example, staircase. We thought about what happens before you end up on the top stair. What is the last thing you did? Because that's the thing we can actually get a handle on. There's too many possibilities to go from the bottom of the stairs to the top, but the last move, there are very few choices in which we can make the last move. So similarly here, we're going to think of the last move that we have to make before all of the discs are actually repositioned onto the new tower. You cannot put the largest disc on top of anything at all, right? In the case of 3 here, the only way I could move the largest disc was when it was by itself and there was an empty spot, an empty pole to put it on top. Otherwise, I can't move it anywhere because it can never go on top of anything else. It's larger than everything else. So my largest disc is going to also be the key to this process. You can't put the largest disc on anything but the very bottom, so that has to be a move all in itself. So now we can think about breaking this problem into smaller ones. Let's generally think of the strategy. What I would like to do is I would like to move K discs from pole A to pole C. This is my goal here. How can I accomplish this task? Well, this task consists of several things. Again, because the largest disk has to move all by itself, I can think of, okay, well, this guy will have to move all by itself, but in order for me to move it, I had to move the top K-1 disks off of this pole first. So, what I first have to do is to move K-1 disks from pole A to pole B. After I did that, so let's say all of these guys, this entire substructure ends up on this pole here. So they're sitting pretty out here. Then I can move my largest disk over to pole C. Okay, that's my next step. And after I've done that, I'm going to move this entire tower over to be on top of it, right? So this, and then I am going to move my largest disk from pole A to pole B. That's my next task. And then what's going to happen is I've reduced the problem to the smaller one. Because again, now this entire stack sits over here. There are K-1 disks and I have to move them to the last pole. If I can move K-1 disks in a certain number of ways, that's the number of ways to do it. So, move K-1 disks from pole B to pole C to be on top of my largest one. So the total number of ways to move K disks from A to C is the number of ways to move K-1 disks from A to B plus move the largest disk from A to B, plus move the other remaining K-1 disks from B to C. Now we actually have to think of what are the corresponding numbers. So remember that we've defined an actual function for the recursion. M sub n is the minimum number of moves required to transfer n disks. So moving K disks is M sub K. Moving K-1 disks is M sub K-1. Moving the largest disk, just one disk from one pole to the next, when it's the only one there is only one way of doing that. Plus, there are K-1 disks that we still need to move. Actually, the exact same ones, right? So we took these, we plopped them in the middle, then we moved the largest disk over, and then we have to plop the exact same K-1 disks over to the last pole. which means it's actually the exact same number. Okay, and so now what do we have? I have mk is mk minus 1 plus 1 plus mk minus 1. Well, I can actually see that two of them are similar terms. So mk is 2 times mk minus 1 plus 1. And that is my recursion. Except, as before, I'm not done quite yet. I need an initial condition. So what are the minimum number of ways to move one disk from one pole to another? If all I have is one disk, all I have to do is pick it up and move it to another pole. How many ways are there to do that? Exactly 1. So m of 1 is 1, and then altogether I have myself a recursion that actually describes how many ways there are to solve this puzzle.